tools contain a few modeling components, including a GIS layer, a model input application, and the system dynamics simulation engine built in Python. This model demonstration will guide you through the full process of setting up a simulation and running the model. The GIS layer of the model is built in Esri ArcGIS. To apply the model to a new project, users have to define the urban form in GIS. To avoid too much details of simulating every specific buildings, users need to come up with a library of generic building and land use types to represent the urban form. The definition of generic building and land use types can be based on the usage of buildings, the envelope design of the buildings, the shape of the buildings, and etc. In this case, 7 building and land use types were defined. Other than building and land use types, users can define other geographical zones and networks such as transportation zones, transportation network, energy demand zones, water demand zones, and so forth. These geographical zones are defined based on actual context of the project. For example, the definition of water demand zones will be depending on the water distribution system. The definition of transportation zones will be depending on the transportation network design of the project. After defining the geographical zones, system-level facilities that serve the project area need to be defined in GIS. These facilities include water treatment facilities, solid waste processing facilities, energy supply facilities, and so forth. They can be outside of the project boundary, and defining them geographically within GIS will later provide further inputs to the system dynamics simulation engine. For example, the distance information captured in transportation network will be imported to the system dynamics simulation to account the energy consumption in transportation. After defining the urban form in GIS, the generic building and land use types will be simulated in a building energy performance software called eQuest. By inputting the detailed parameters on envelope design, schedule of operation, area usage, and other building performance parameters for each type of building and land use, the tool is able to generate hourly energy demand of these generic building and land use types, which will be later imported to the system's dynamic simulation engine as energy demand. After defining the urban form in GIS and simulating the energy demand of building and land use types in eQuest, users can define other decision variables and technologies in the model input application developed in Microsoft Access. In the home screen, different alternatives are listed. Alternatives can be added or deleted. By selecting the alternative, users can go into the details of each simulation and define the decision variables and parameters within different sectors. For instance, to define the solar panel technology within mixed-use alternative, we can click Energy sector in the navigation bar. Under Supplies, user can select the tab Solar Buildings, which they can turn on and off solar panel technologies, specify the roof area for installation, and choose specific solar panel technology to apply. Similar to this, the model input application contains user interface to input parameters for water sector, solid waste sector, and so forth. After setting up the model input application, let's turn into the system's dynamics model in Python. This is the key simulation engine in the urban systems modeling tools, which provide us with hourly quantitative simulation results. The screen you can see now is the root diagram of the model, which consists of 6 sectors including water, energy, transportation, solid waste, urban form, and urban ecology. Each symbol on this diagram represents a variable of the model, and it can contain multiple dimensions to serve like a matrix. The links connecting variables represent the actual mathematical interrelations in between. For instance, to supply potable water to community, it needs to be treated in advance at the water treatment plant. The amount of water being treated requires electricity consumption, which becomes an energy demand within energy sector. Each of these sectors contains complex systems dynamics modeling that capture all the mathematical relationships within the urban systems. Let's zoom into energy sector to take a closer look at some details of the model. As mentioned earlier, that each of these symbols on the diagram represent an actual variable in the model. On the model diagram, mathematical formulas or functions between the variables can be seen by double-clicking one of these variables. For instance, here energy produced by solar panel on top of the roof area is calculated by multiplying the roof area, efficiency, and correction factor, as well as hourly solar radiation data. All the information that we previously defined in GIS and model input application can be pre-processed in database and eventually imported to the model in PowerSim by clicking the Load button. We can run the model simply by clicking the Run button and view dynamic outputs of any of these variables in the model. Again, let's look at the energy produced by solar panels. Here you can see the energy produced by solar panel during every hour in the simulation year. The hourly solar radiation data brings in the variation of energy output during the day, which can be utilized to explore the operation of smart grid, peak management, etc. The outputs of other variables such as water storage at the rainwater harvesting tank, the water usage from on-site alternative supply, energy consumption by solid waste processing facilities, greenhouse gas emissions by transportation mode, can be all produced at hourly time step in the systems dynamics simulation. In summary, the urban systems modeling tools serve as a virtual laboratory which enables city planners to view and evaluate many planning options and make confident decisions before committing capital investment.